Question appeared for GATE 2016 1 mark. Assume all the digital gates in the circuit shown in the figure are ideal. The resistor R equal to 10 kilo ohm and the supply voltage is 5 volts. Implies logic 1 is treated as a 5 volt. That if flip-flops D1, D2, etc. up to D5 are initialized with the logic value 0, 1, 0, 1, 0. The clock has a 30% duty cycle. The average power dissipated in milliwatts in the resistor R is. So this is actually a ring counter. The last output is fed back to the input of first flip-flop. So let me write outputs of different flip-flops Q1, Q2 and Q5. Their initial values are given as 0, 1, 0, 1, 0. In the first clock cycle, it will change the state. Similarly, second, third, fourth, fifth, etc. So initial values are 0, 1, 0, 1. So it's a shift register. Its value content is shifted towards right by 1 digit. And Q1 it is modified with the initial value of Q5. So Q1 is modified with initial value, that is Q5, that is 0, and the entire pattern will shift towards right by 1 digit. Just after second, Q1 is modified with Q5, the entire value is shifted towards right by 1 digit. Right. So you can observe that just after fifth clock edge, the initial pattern 0101 will repeat. And also you can note that if Q1, Q2, Q3, Q4, Q5 are repeating after 5 clocks, then the value Q3 or Q5, here it is Q3 or Q5, also will be a periodic, or it will repeat after fifth clock cycles, because Q3 and Q5 are repeating after fifth clock pulse. So the voltage across the resistance R 10 kilo ohm also will repeat after 5 clock pulses. And let us identify the value of Q3 or Q5. Q3 or Q5 will be 0 initially, because Q3 and Q5 are zeros. So Q3 or Q5 will be 0. Then both are 1. Just after first clock edge it goes to 1. Second again back to 0. Third clock edge Q5 is 1, so it switches to 1. Fourth clock edge switches to 1 or continues in logic 1, because Q3 is 1. Again, just after fifth clock edge it goes back to 0 or 0, 0. It repeats. So for a given period, that is 5 times clock, the OR gate's output is logic 1 for 1, 2, 3 clock periods. Right, 3 clock periods. So the power is defined as Vrms square divided by Vrms square divided by R, or simply V square by R, and Vrms is defined as 1 over T mean value in hours, T root mean square value, square of the voltage waveform. Voltage waveform is 5. So 5 square is 25 Tt upon R, and this numerator is actually Vrms, root mean square value. We should square it. So that will turn to be 1 over T integral 0 to T 25 dt upon R. So as I said, the total period of the waveform Q3 plus Q5 or voltage across R is 5 T clock. So 1 by 5 times T clock integral over the period, that is 5 T clock 25 dt upon 10 key. And you can verify that 1 over 5 T clock, and you can see that out of 5 t clock cycles, the voltage waveform is at logic 1 for 3 clock cycles. All other cases, it's at logic 0. So you can integrate for 3 clock cycles, 3 t clock. So waveform for first, third and fourth clock periods are identical. So you can integrate from 0 to 3, or you can integrate from 0 to t clock, then multiply it with 3. Both are correct. So anyway, 25 tt. That will give me 25 multiplied by 3 t clock upon 5 t clock. And I should not forget 10k resistance here by 10k. Also you can note that this is square of the waveforms, that is 5 squared, and t clock and t clock will get cancelled. So 3 by 5, that is actually a duty cycle of my voltage that is appearing across the resistance, that is Q3 or Q5. So to identify the power dissipated in a resistance is nothing but voltage square multiplied by duty cycle by the value of resistance. You need not do these things. Or we can also say that you square the waveform, then it will become 25. Instead of 5, it will become 25, and that 5 is active for 3, 2 plus 1, 3 clock cycles out of 5, right? So 3 periods, 2 periods here, 1 period here, 1 and 2 continuously 1, so 2 clock periods, and the amplitude is 5 square, that is 25. So its average value is 25 multiplied by on time. On time is 1 clock period here plus 2 clock period, that is 3 clock period, divided by total period is 1, 2, 3, 4 and 5 clock period. So voltage square multiplied by duty cycle, or Vrms square divided by R. You have to calculate Vrms. If it's a constant waveform, pulsating waveform, both are identical. This is reduced to this form. So anyway, it is 25 multiplied by 3 by 5 divided by 10k. That will come as 3 multiplied by 5 divided by 10k. That will come as 1.5 milliwatts. So right answer is 1.5 in milliwatts. The question appeared for GATE EC 2022 marks. The state diagram of a sequence detector is shown below. The state S0 is the initial state of the sequence detector. If the output is 1, then 4 options. The sequence 01010 is detected. The sequence 01001 is detected. The sequence 01110 is detected. The sequence 01011 is detected. So by observing the state diagram, you can see that along with the transition arrows, they have given 1 bar 0, 0 bar 0, 0 bar 1, etc. So this first index corresponding to the input, the second index is corresponding to the output. So they have mentioned that if the output is 1, then which sequence is detected. And you can see that the output is 1 for a transition from S4 to S3 only, right? All other cases output is 0, right? Output is 0. So we should start from the initial state and we should come to S4, then we should go back to S3, then you will get an output equal to 1 and the corresponding sequence will be detected, right? So let us start from initial state as 0. We have an input 0, so I'm writing 0 here. I'm going to S1. I should reach S4, so I should cross S2. I cannot go this way, the arrow is reversed, so I can go from left to right. Okay, so S1, then I'm going to S2, the input is 1, so I'm writing that. I'm going to S3 with input 0. If the input is 0, I'm going to S3 state. If the input is 1, I'm going to S4, so I'm writing 1. And again, if input is 0, I'm going to S3 state, back to S3 state with output equal to 1. So the sequence detected is 0 1 0 1 0 0 1 0 1 0. So to identify the input sequence, I have a 0 1 0 1 0 0 1 0 1 0. So the first option is the right choice. Next question is appeared for GATE EC 2017 2 marks. The state diagram of a finite state machine FSM is designed to detect an overlapping sequence of 3 bits is shown in the figure. The FSM has an input in and an output out. The initial state of the FSM is S0. So it is called a finite state machine, implies it's a sequential circuit or a sequential machine with a finite number of states, and it is given that the initial state is S0, right, and the sequence is prescribed, and starting from the leftmost bit, that is from here, then the number of times out will become 1 is. Okay, so I'm starting from state number 0 S0, and my input is 1. So if input is 1, I will go to second state with output equal to 0. Then comes input 0. If input is 0, goes to S2 state with output equal to 0. Then comes 1 again. Then I goes to third state, S3 state with output equal to 1. So I have a 1 out. Then comes 0. Here 0 comes, I am going to S2 without 0. Then comes 1. 1 comes means I will go to S3 back again with output equal to 1. So I am writing a 1. Then another 1 here. So another 1 implies I will go to state S1, right, without equal to 0. Then comes 0. Then in 0, out 0, I will go to S2 state. Then comes another 1. Then input is 1, I will go to S3 without 1, so I will write a 1. Then comes a 0. Then comes a 0. 0 means I will go to S2 state. Input 0, S2 state without 0. Then comes another 0. Another 0 implies I will go to the initial state back again, S0. Then comes 1. I will go to S1 without equal to 0. Then comes again 1. I will go to, then comes 0. I will go to S2 state if input is 0. Then comes a 1. I will go to S3 state again with output equal to 1. So I have 4 number of 1s at the output. So output will be 1. The number of times output will be 1 is nothing but 4. Okay, or you can do this in another simple way also. That is, you are having output equal to 1 only here. So if you are starting from initial state, input equal to 1, you are moving to next state. Then if input equal to 0, you are moving into next state. Again, if input equal to 1, you are moving to the last state with output equal to 1. That implies you are detecting actually a sequence 1 0 1. So in the given pattern, 1 0 1 0 1 1 0 1 0 0 1 1 0 1. So this was a given pattern. 1 0 1, another 1 0 1 overlapping sequence, then another 1 0 1, third case, then fourth case is 1 0 1. So we are having 1 2 3, 4 times you will detect a 101. So output will be 4. Period for gate EC 2017 1 mark. Consider the D latch shown in the figure, which is transparent when its clock input CK is high and has a 0 propagation delay. It's a D latch. In the figure, the clock signal clock 1 has a 50% duty cycle. So this is having a 50% duty cycle, and clock 2 is 1/5 period delayed by or delayed version of clock 1. So clock 2 is delayed version of clock 1. Shapes are similar, and it is shifted by T clock by 5, that is 20% of the time period. The duty cycle at the output of the latch in percentage is this output signal duty cycle is asked. So we should plot output signal first, then we can easily identify its duty cycle. So before that, let me draw the clock 1. Clock 1 is a 50% pulse waveform equal on and off periods. 50% of the time period is on and 50% time period is off. And clock 2 is a shifted version of clock 1 by 20% of the time period. It's a shifted version, so time period of both waveforms are same. It's only a shifted version. So this is clock 1, this is clock 2, right? And you can note that this is 50% of the total period T on time. And the property of a D latch is that clock should be high, then output will be equal to D input, that is clock 1 itself, right? So effectively the output will be at logic 1 if both clock 2 and clock 1 are at logic 1 simultaneously, right? That corresponding to this shaded area, during which both clock 1 and clock 2 are at high state, right? And you can also notice that this area or shifted region is corresponding to T clock by 5, that is 20% of the total period T, right? So if you are plotting the output up to this point, again up to this point, again up to this point, it repeats. This blank area is 20% of T, so that 50% of T minus 20% of T, so this will be 30% of T. So this is the output waveform, and the period of the waveform is same as T clock, no change, right? T clock or T. 3 waveforms will have same period. So the duty cycle of the output signal is on time divided by total period. On time is 30%, that is 0.3 times the period, divided by total period is T. So that is T on upon the total period. That is my duty cycle, right? So this will cancel each other. So in percentile, it will be 30%. So the right answer is 30. The question appeared for gate 2017 1 mark. In the latch circuit shown below, the NAND gates have non-zero but unequal propagation delay. The word unequal is important. The present input condition PQ equal to 0, 0. If the input condition is changed simultaneously to P equal to Q equal to 1, then output X and Y are, right? The initial values are P equal to Q equal to 0, and that will guarantee X equal to Y equal to 1, because both gates are NAND gates. If one input is at logic 0, the output will be different at logic 1. Then simultaneously we are changing P to 1 from 0 to 1, Q also from 0 to 1. Suppose the upper gate changes quickly or the propagation delay of the upper gate is low compared to the lower gate. Already y equal to 1, that 1 is available here. P is already 1. Both inputs are 1. So quickly x will changes to 0 if the propagation delay of the upper gate is low compared to the lower gate. And that 0 is available here and the lower gate remains in one state. Let us assume the other case. If lower gate changes its output quickly, then P is 1, Q is 1, right? Initial both outputs are at 1, so I'll have a 1 here, I will have a 1 here. So both inputs are 1 and lower gate switches quickly. That will give me a 0 here, and that 0 will be available here after some time. Then x will be at logic. So depending on the propagation delay of the individual gates, x can be 0, y can be 1, x can be 1 or y can be 0. So either x equal to 1, y 0, x1, y 0, or x 0, y 1. So second option is the right choice. This question appeared for GATE 2018. A traffic signal cycles from green to yellow, yellow to red, and red to green. In each cycle, green is turned on for 70 seconds, yellow is turned on 5 seconds, and the red is turned on for 75 seconds. Then it should repeat. This traffic light has to be implemented using finite state machine. The only input to this FSM is a clock of 5 second period. The minimum number of flip-flops required to implement this FSM. It's a GATE 2018 EC question, 1 mark. So here we are having a machine, finite state machine, or a counter, or a timing circuit that will generate yellow, green, red signals for a proper interval. So the total interval is 5 plus 70 plus 75, that is 150 seconds. You are controlling this circuit, logic circuit, sequential circuit with a clock of 5 second period. So for each clock it should perform the action green to yellow, yellow to red, and red to green, right, before the occurrence of next clock. But the problem is the clock will repeat for each and every 5 seconds. So in one clock time interval, the entire action of sequential circuit will not be completed. So you should scale down your clock frequency, or you should scale up your clock period. The factor by which I should scale down the frequency is given by 150 divided by 5, that will give me 30. So I should use a mode 30 counter. A mode 30 counter can be implemented by using 5 number of flip-flops. 2 power 4 is 16, 2 power 5 is 32. So 30 lies in between 16 and 32. So I should use 5 number of flip-flops. If you are using 5 number of flip-flops, you will have 5 different outputs for flip-flops Q5 to Q1, in which you can make use of 3 different outputs to control green, yellow, or red lights.